Okay.
Oh, is my voice not clear?
Oh, it was just there was a little bit of feedback in the. I don't know if that's me or you.
Could be you. I was
Oh.
not talking.
Okay. Well,
Now is it okay, sir?
yeah, it's okay.
Yeah. So I can start sharing my screen and we'll start my presentation.
Yeah.
So please give me a second.
Okay.
Yeah. So I think you can see my screen now.
Yeah, I can see.
Yes, sir. So this presentation is about my project GSOC 2019 project with INCF. I worked with the OpenWorm Foundation, which is a sub-organization of INCF, and within OpenWorm there's a group called DevoWorm Group, in which I have worked. So my project is basically this semantic image processing for developmental data science, and my mentor for the past 3-4 months was Bradley sir. And let me give you a small introduction to the project. This is the contents, like what how the presentation will be. This is the introduction. First, I'll give some introduction to the project, and we'll explain what was our initial plan, like when we were about to start coding, what was our plan, and what has been accomplished after 3 months of coding, and the future scope of this project. This explains like how the project can be improved, or where this project will be useful in that ways, and where to follow includes the links to where to find the project, where to find the code, where to find the documentation and all. So let's get started with the introduction to the project. First of all, introduction to the project, I must mention the DevoWorm Group and the OpenWorm Foundation. DevoWorm Group is a special interest group of OpenWorm Foundation where we try to understand the developmental dynamics of a microorganism, mostly C. elegans, like how is it evolving as an organism, and everything. Uh, and This is my this our project. Basically, what we wanted to do is that when we get the microscopic videos of embryogenesis of C. elegans, we need to create a software which can automatically segment the cells of the embryo. That too semantically, like semantically in the sense, like in an image, like each pixel will be given a label. So we tried with 3 labels. One label is for the background, one label is for the cell region, and other label is for the cell boundary. So basically each pixel in the image, like in the input image, will be given a probability where that like it will decide the pixel belongs to which label. Let's say for the pixel at 0th position of an image, like of an input image, which contains the cell, which contains the cell dividing, which contains a time step of embryogenesis movie. So that image will be that each pixel of that image will be having a three-dimensional probability, where it will where the pixel will be having, like whether the pixel is a foreground pixel, whether the pixel is a background pixel, or whether it's bound to be on a boundary and all. So that's basically what semantically means here. So that was the main aim, and this is an extension to the GSOC 17 project. In 2017, OpenOne had a student work on the same problem. Back then, it was not a semantic approach. It was mainly classical techniques. Like these are the classical techniques that have been tried. Edge-based methods, these level sets algorithms, and these major classical techniques. And out of these, level set algorithms were the best. Like in the report, after the 3 months of the project, this was found to be this was giving the best results, but there was scope to improvement. So that's why this project again came in this of 2019. And so what was initially planned before the coding period started? So what I proposed is that the main problem, the actually to do semantic approach, semantic segmentation, we need deep learning for that. And for deep learning, like for machine learning also, we need labels. Like let's say we have an input image and we'll have an label image where like that will be our training data. Like if we have some thousand images and their corresponding labels, then we can teach the machine that when such an image comes, this is how the label should be. And then the deep learning model goes through all those images and it will update the weights inside it. And when a test image is seen, it will try to predict the label of that new test image which it has never seen. So basically, that is what deep learning does. But the major setback here is that we don't have any label data. Like we have around 3,000 images and of 3,000 frames from movies, microscopic movies, but none of them have labels. So what I propose to do is that I propose to do an unsupervised image segmentation and as well as a semi-supervised image segmentation. Now the unsupervised image segmentation is nothing but trying to do the segmentation without the labeling part, like without the labels from the in the training data. So I found a paper called WNet paper. It's on arXiv. Basically, it proposed deep learning architecture where we can segment any kind of images in an unsupervised way, basically without labels. And also, I proposed to do a semi-supervised image segmentation where there are only uh, like basically what I initially planned is that for the first phase, if I was able to do this unsupervised image segmentation, then I could have generated the labels for at least 500 images, and then I thought I could use it for semi-supervised image segmentation because semi-supervised image segmentation is nothing but, let's say we have some thousand images and we have only labels for 500 images in our training data, and semi-supervised approaches come into place when we have training data as such, like only half the data is labeled and the other half is not labeled. So we try to label the unlabeled part of the training data set, and uh, then we try to create a whole data set which in turn will be fed into a deep learning model so that we'll be getting good results. This was planned for phase one of the project, and this was planned for phase two of the project. And for the phase three, we thought of like when we started, we did not actually have a very nice idea of what might be a good thing to do, but we thought of figuring it out like when the phase three comes. So basically, what we wanted to do at that time was to create an analyzing software, like when a microscopic movie uh, of a microorganism is given, we wanted to analyze it somewhere and provide insights to the researchers, like a software which takes in the video as an input and gives out the analytics, like where is the cell position, where is the centroid of the cell, how many cells are there, that kind of tracking. So basically we wanted to do that. That was the initial plan. And what has been accomplished? So I spoke about this WNet convolutional autoencoder, right? So it is the unsupervised image segmentation So what the so basically what happened is that when I tried to implement this wnet convolutional autoencoder, I faced some problems with deep learning for J. Actually, I wanted to implement this as an ImageJ plugin. Like there's a tool called ImageJ, and then I wanted to create a plugin so that all the users of ImageJ can directly use that plugins to do the semantic segmentation. So all the deep learning stuff, the all the deep learning stuff that I have to do is basically more inclined towards Python because it has more ecosystem for deep learning. So what I plan to do is that I will train the models in Python. I will write the models in Python and I will train the models in Python. And I will download the model. I'll save the model and then I will import it to the ImageJ plugin. But ImageJ is written in Java, so I had to make an interface between the Python code that I will write and then the Java code that I'll write for the plugin. So then I found out there's a tool called Deep Learning for J, which will help us to import deep learning models into Java applications. So the problem here was to which I faced is that basically I tried to implement this in Keras initially. Keras is a deep learning library for Python, and then in that I can show you the implementation once. Here I train the models. I train the models here. This is Kaggle, which will provide GPU for that because in my system there is no GPU, so I needed a GPU for a very. This is a very large model actually. So I have written the code here. I have written the code on Kaggle. I have trained the models here, and then this is how the output looked like. So what I did is I have saved the model here. I have downloaded it to my local system, and then I used uh, deep learning for J. I took the help of deep learning for J so that I can import the saved model into this ImageJ plugin. So basically, what you see here is the ImageJ plugin code, and there are functions to load the TensorFlow model and functions to get the output, like predict the output of a test image and all. So so basically, that was the thing. The problem with initially what I faced was with Keras. There was a slight problem with Keras and deep learning for J because I had to use some custom layers, custom convolutional layers, and that has been a problem. So after going halfway through that, then I realized that it is not possible to import Keras models with custom layers into Java applications with deep learning for J. So what I had to do is that re-implement this whole model in pure TensorFlow. So TensorFlow is a machine learning framework by Google itself. So I had to do it. I had to completely implement it in TensorFlow and then use deep learning for JS support for TensorFlow so that I can import the saved model into Java applications. So that took a lot of time, and I was only able to implement the. I was only able to implement the unsupervised image segmentation, and we have skipped the semi-supervised image segmentation uh, because basically we wanted to the aim of both the unsupervised and semi-supervised approach is the same, as we had many technical problems and then we had less time, so we thought of only going with unsupervised image segmentation. And I want to show a small demo of how this image plugin works. So uh, this is the code, right? This is the code for the plugin. So with the help of Maven, I was able to build this code as a jar application, like jar file, and then this is my installation, PG installation, image installation, and I have placed the jar file generated from this code. I have placed the jar file in the plugins folder of my Fiji installation. So how a user can use this is that one can install image from here, and then download the jar file from here. I have given the link in my final submission, my final project submission on my Tumblr blog. Download this jar file, download this Fiji tool, and then place that jar file, downloaded jar file in the plugins folder of your Fiji. Here is the plugin. Here is the jar file. Now let me show a demo. This is how Fiji will look like when we try to open an image. Let's open an spim image. Let's pick some random image. Now this is the image. Now we wanted to perform semantic segmentation on this image. So I have placed my plugin on this GUI here. Now it's actually loading the model, and it's trying to predict the output. We'll get the results about less than 1 minute. Here. So basically, the model understood all this region as the background. That's why it gave the green color, and it gave the cell regions as the red color, and it gave blue color to the cell boundaries. Of course, there's scope for improvement here, but then as we did not have time, this was how much we were able to do. This is how you will use the plugin. Um, this was one part of the project, and the other part was to, as we discussed earlier, we wanted to create a software where we'll take the input images of this microscopic embryogenetic images, and then we try to find how many cells are there in the image, how many, like, where the cell is located, what is the xy coordinate of the centroid of the image, what is the area of the cell, and all. So what we thought is that we made a web app. Using Python, using Flask framework, and then deployed it to this link, OpenDevCell.herokuapp.com. One can go here and upload images, and then can download the processed images and also a CSV file containing the analytics of the image. Let me show a demo of that as well. This is the website that we built for the phase 3. So basically what we can do is that we can upload our images. Let's select some, we can upload multiple images. Let's select some random images here. Let me open it. Let me upload them. So this is how the result will look like. You can see each of the input image. On each of the input image, the cell boundary has been detected and the cell centroids have been detected. Now you can download each of these processed image. Let's say I want to download this image. I can the image is downloaded to my system here, and then we'll be able to download a CSV file. The CSV file has the following contents here. Let me show it. This. Now I have uploaded two images, right? One is the C105 and C107. So in this Excel, in this CSV file, what we'll be having is that the name of the image, number of cells in this image, and the XY coordinate of each of this image, and the area of like XY coordinate of each of this cell, and then the area of each of this cell. Now, from this data, we can say that the uploaded image C105 has about 10 cells, and each of this cell has the XY coordinate recorded in this file, and also the area. So basically, this is what the web app does. It can provide the XY coordinates and the area of each of the cell. So that is what has been accomplished. One is this website where we can upload images and can get the centipedes of each of this. And the other is a image plugin which can do the semantic image segmentation using deep learning. And what is the future scope of this project? So when I tried the WNet architecture, the unsupervised architecture, deep learning architecture for semantic segmentation, so it was not very perfect. Like there is really scope for improvement. It's actually a huge model, so now we can try out different techniques on that. We can try out different sets of parameters, like see where the image is, neat, like where the output is perfect, like and stuff. So we can try out different architectures of deep learning as well, and then and then we can also improve the website in a way where we can automatically tag the cells. What I'm saying is that um, now as we have this kind of data, so we also have reference CSV data which Bradley sir has provided me. So in that CSV data, what we basically have is that the average the average cell positions and the cell names of C elegans, like the average of many videos. It has been an average values of many videos. So what we can try to do is that we can put that as a reference CSV file, and whenever a user uploads his video, we can try to we can try to we can try to make our algorithms work on it, and then we can try to compare the XY coordinates of the input video and the reference video. Let's say we have in our reference video, let's say we have some XY coordinates of a cell, and then also we have a time at which the cell is born. Then we can try to identify at like if we detect a cell at that coordinates, then we can try to match it. Like we can say that, oh, this cell is at this coordinate at this point, and also we have the same cell, we have a cell named ABA in our reference CSV data, so this must be ABA, that kind of thing. Like we can name the cells in the user inputted video as well. So we can try to automate the process of cell tagging as well. And that is the future scope of the project. And where to find the project. All the code has been pushed to the DevoWorm into the GSOC 2019 project of DevoWorm user, and we can find the micro reports over here on neurostars.org GSOC 2019. Like this is where I wrote my weekly reports, like how much I have done over the past 12 weeks or 13 weeks. And then I have written some weekly reports as well on my Tumblr blog. On my Tumblr blog, I have written the final blog and also the phase one a blog for phase 1, phase 2, and phase 3 as well. In each of this coding, I have divided the blog into few sections. What has been done, issues faced, and what are the solutions that I have taken. And each of these phases blogs will be having that. So we can go through that, like, to see what all technical challenges I ran into and what all the solutions that I came up with, and what can be improved if this project comes again next time. And also over the last 3 months, so I had been discussing my problems and issues with Bradley sir over such meetings, and all those discussions can be found in the YouTube channel for DevoWorm. So there, yeah, there as well you can find the progress of the project, the 3 months of the project. And then if you have any questions, I'll be happy to answer.
Yes. Vinay, could you put your last
Yes.
segmented image on the screen, please? With the green lines showing.
This one?
Let's see. Yes.
Yes, sir.
Yes, that one. Okay, I've got a couple of questions. Can you determine separately from the cells the boundary of the whole embryo?
Sir, sorry, I couldn't hear. Can you repeat, please?
Okay, I'll put it in the chat. Okay.
Yeah, thanks.
The boundary of the whole embryo.
Yes, sir, I can. So there's in OpenCV there's a method where we can get the entire boundary as well, like the whole. Like, you wanted a boundary for this image, right? Like this boundary, right?
Yeah, all the way around the embryo, right?
Yeah, we can get, sir. So basically, I intentionally did not include that boundary. Initially, when I tried to use OpenCV for this thing, I also got this boundary as well. But then that is also being counted as a cell, like this cell. Like here, there are only 10 cells. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I include this boundary as well in the code that I have written, it will take the number of cells as 11. So I intentionally avoided this boundary being detected. We can actually get this, sir. It's a small task.
Okay. Second, the green lines represent the cell boundary.
Yes, sir.
Okay. Now those frequently, if you took a line from the centroid of the cell out, that line would cross the boundary sometimes more than once.
Yes, sir.
Right? Okay.
Yes.
Okay. There are two possibilities here. One is to take a line from the centroid out in small angular increments, and at each one take the point that's furthest out, and start the other points. That would give you a curve that is a function of a polar coordinate. It would give you a function of a polar coordinate in general, unless the cell itself has some convexity.
Yeah.
So you could consider doing that. The other thing you could look at is the convex hull of the curve.
Oh yeah, I initially also considered that as well, because I was trying to refine this boundary lines.
Yeah.
But then when I was I figured out the method a bit late, so I was actually short on time, so I couldn't do it. But thanks for the feedback, sir. I'll definitely try it out.
Okay, let me ask this question of time. Are you finished with working on DevoWorm, or are you going to continue? I don't know what you're doing.
Yes, sir. I'm willing to continue and contribute in any way as well. in any way possible.
Okay, so let's think this through a little bit more. Consider two adjacent cells.
Yes, sir.
Okay?
Yeah.
If you took the line between their centroids.
Okay, a line like this.
Okay, a line like that. That would be fine.
Yeah.
Then with the boundary established or approved with a convex cell or something like that, you could now extend each boundary towards the other cell until you hit the membrane.
Oh, okay, yeah.
Okay?
Yes,
You
sir.
see what I'm saying? And you could do it in increments. You could do them both, well, whatever. You could extend them both towards each other along the center.
Yeah.
Now,
So the maximum region will be covered.
well, that's just one line. Let's say just take the one line between two centroids.
Yeah.
So along that line, you could improve the boundary by pushing each one until it hits the membrane. Okay.
Yeah.
Now the problem is that if you go to, let's say you take the intersection of those two cells with the one above. Okay.
This one.
Yeah. Now you can, if you went along the membrane, you could go until you reach that triple intersection. So you could do the same thing. In other words, draw a line from each centroid to the membrane for each pair of cells, but you stop when you hit an intersection of three cells.
Yes.
So again, you could improve the boundary and bring it up to the membrane.
Yes, sir.
Okay.
Understood.
Now, I'm a little confused. How come you don't use the membrane boundary itself?
Sorry, sir, I couldn't hear you.
Why is the green line different from, I guess, the blue lines?
Oh, in the previous,
Do you have a picture?
blue line?
Yeah, do you have a picture of the same section with the blue lines?
Oh, that one, yeah. That was basically...
The blue is never a line.
Yes, sir. Oh, in that image, let me show you such image. In this kind of image, right?
Yeah. Okay.
So
can you magnify that, please?
Yes, sir. Let me see if I have it saved somewhere. So can you see
Okay,
it?
I see. So the blue is not as reliable as the green line because it's full of holes. So it's not.
Yes, sir. Basically, what this result is that this result is this came as an output of WNet architecture. So in that deep learning process, as this is an unsupervised way, I found it hard to tell the machine that this is exactly the boundary where you need to bisect it. So even if the brightness is a little bit increased, so it's not working properly. Basically, we kind of choose a less efficient model, I believe, after trying to implement that. So I put this aside after the first phase, and then I went with the classical morphologist techniques, where you can see this kind of outputs.
Okay, I see. So the green lines are much more reliable than the blue.
Yes, sir.
Yes.
In this, this is actually semantic segmentation. Like if you look closely, each of this pixel here will be given a probability where the pixel will belong to the red color or the green color or the blue color. As the input images has some noise kind, like it has a white foggish shade over those images. So basically, it was difficult for the deep learning model to try and exactly find out which label a pixel belongs to. And as we don't have any labels as well, like in the training data, so that was a difficult task to do. So that's what I mentioned in my future aspect of this project as well. So if we wanted to try to improve this project, we can try a more reliable deep learning architecture. We have to do some research on that. Like we have to go through the research papers and see how the metrics like how they have defined the metrics and how well their model is performing, and try to implement that deep learning architecture on our data set. So basically we need to do that.
Okay, but if you go back to your picture with the green lines, it's obviously superior.
Yes, sir.
So maybe maybe the thing is stick with algorithms that work.
Or if we had some labels, like if we had the time to manually label them, then if it will become a supervised deep learning problem. So then there are very good like with like very good state of the art deep learning models where will get like very good results. Like Google has always been doing that, and Facebook has always been doing that. Also, if we can do that, we don't need to implement our models only, because Google has some pre-trained models. Like they have trained the models on different data sets, and they have saved those models. So basically what we can do is that we can take that saved model, and we can train that model on our data set. So then this model will be able to segment the cells more neatly. Let's say now if we see the state of the art for supervised segmentation, now there's something called mask RCNN, which is for semantic segmentation. We can basically try to do that if we had some labeled images. But as we did not have any labeled images, this was a really challenging problem that I feel. And there was not much research paper. There are not many research papers which try to segment images in an unsupervised way. So if we had the time to manually label some images and try out how this can be, maybe deep learning can outperform this classical techniques as well.
Okay, but if you look at this one, if you expanded the green lines until they met the membrane,
Yes, sir.
then you could use that as a mask to throw away all of the blue which is on the membranes.
Yeah, that is an option, but even this might not be an accurate 100% accurate solution. In some images where it might like if this smell is more smaller, then this algorithm might be able to like might miss that as a cell. It might not recognize that as a cell as well. So even this method is only some 95% perfect or something like that. So if you can try to like you said too, we can try to improve the membrane region, and then we can try to use those as labels as well. But before feeding that into the model, we need to manually check how good they are, because the model can be only as good as the data set we are providing.
Mm-hmm. Okay, looks very good. I mean, it's a great start here.
Yeah, thanks.
Okay.
So yeah, thanks, Vinay. That was a very good presentation. Jesse came in the middle, so does Jesse have any comments that you wanted to make on the presentation, or? Okay, yeah, good job. So I guess I had a couple questions, and I've seen this work before, so I know what's going on pretty well. But so you have the web app, so when we use the web app, you would take an image and you would upload it, and it would segment the. So do you have to do any prep for the images before you upload them, or is this just you can upload an image, a microscopy image, and get a result?
So most of the pre-processing I have done. So basically, the cases I have considered is that the input images can be of different sizes. So whatever the user input, like let's say a random user tries to upload an image. So this app will take in that image and it will resize it to an image where my algorithm is working perfectly, so that it will not miss any uh, it will not miss any cells, like even if they're very small. Like even if they are very small, the algorithm might miss some cells, but mostly for what I have tested, it did a good job. And then the other case that I have considered is that the brightness levels might be different. So when the brightness levels are different, it's difficult to try to like see where the boundary is. So what I did is I extracted the hue channel. Like the user will be uploading the RGB images. So in this web app, what it will do is that it will take in that image, it will convert it into HSV color space, and then it will extract the hue channel of that image. So basically, we are trying to eliminate the effect of brightness. So when we increase the brightness of an image, in the HSV color space, the V channel, HSV, right? The V channel will be affected by the brightness, but the H channel won't be affected. So even if there are slightly darker images, or if there are slightly brighter images, as we're dealing with the HSV color space and we're extracting the hue channel, I think most boundaries will be detected. So basically, I considered those two scenarios where the randomness will be.
Okay. And then, what is your? You said that you were looking a little bit into like deep learning approaches and things like that. What is your opinion on like how you
Yes,
could improve the performance? What
so
direction?
basically, I also during the implementation process, I've asked for help also to see how the unsupervised ways can be improved. So the some advice I have seen on the internet, like on Twitter, and where they have advised is that the unsupervised the unsupervised field is now developing, and it's not yet completely developed where we can completely rely on that. So they kind of advised me to try and get a good data set, and then the model will be perfectly fine. It will be having very good results, very neat segmentations and all. As unsupervised, like trying to like this unsupervised model will be having huge research aspects. Like we need to get into the entire mathematics of deep learning and try to find out how we can improve it ourselves. Like this kind of happens to be a complete research project. So, but if you can have the time to manually label them, or as Richard sir has advised, like we can try to increase these boundaries regions where until where these can touch each other, and if we can see, if we can confirm that that will make a good data, that if that will make a good data set, then we can feed that into our model and see how the results will be. I
Let
think
me
that's the future
let me
aspect.
ask one more question about that. Do you use, or are you thinking about using the information from consecutive slices of the embryo? Uh,
Um, yes, initially also thought of using that, but then I really did not understand how I could use the consecutive frames. Like the segmentation of one image will be like slightly different to the segmentation of the other consecutive frame, right? So
well,
initially I thought, and I searched for research papers, but then at that time I found out that the unsupervised, why not give an unsupervised approach a try and try to find out how the results will be. But then I never got the time to go back there and check how that can be as well. But now as I have time, maybe that is a nice option as well. Like trying to utilize the information of consecutive advantage of consecutive frames. I found some research papers for that, but then I'll have to go through them again, like neatly, see how well
let,
the performance how will be and all.
let me give you an example. I knew a fellow, this is back in the 80s, who was tracing microtubules in nerve cells from serial sections. And he would trace the same microtubule from one section to the next and then to another one. So he went through the full 3 dimensions. Now, here you could take, for example, the intersection point of 3 cells. And you can't trace that through the whole embryo, but you could trace it through a number of consecutive sections.
Oh, right.
Okay? Yeah, so that's a point. In other words, the intersection point of 3 cells is something which has some reasonable persistence in the 3rd dimension.
Yes, sir.
Okay. And therefore might be tracked and usable as additional information for segmentation in the 3rd dimension.
Yes. In deep learning, there's a concept called LSTMs where it will deal with time series data, like let's say a consecutive data, which if we take it at a time step, the data at a time step will be dependent on the data on the previous time step. So maybe we can try that as well. I'll search for research papers including like how we can use that as an advantage.
Okay.
Thanks for the suggestion, sir.
Yeah, now if you go up, you'll see some exceptions here. If you go to the top cell and just below its centroid, there you sort of have 4 cells meeting almost at a point.
Yeah,
okay.
Yes, sir.
So it's an interesting question to what extent you could use these triple points and when they become unreliable. That would be a point where the triple point would be unreliable. Okay?
Yeah. So figure out that as well, yeah.
Yeah, now if you looked at slices above and below this slice, you might see clear triple points, resolving that ambiguity.
Yes, sir.
Okay, so I'm saying these triple points could be very valuable in going to the 3rd dimension.
Oh, all right, yeah. I get it.
So, yeah. Go ahead.
Yeah, no, sir, nothing.
Oh, okay. So, yeah, this is very interesting. And, like, I am maybe planning on doing another, version of this type of research next year, Google Summer Code. So, maybe we can talk a little bit in coming weeks about how to plan for that, because the first one was 2017, and we did some segmentation, and then we built upon that in this year, and so Vinay's done a very nice job of driving that forward. So now the 3rd iteration of it is probably going to explore some refinement or maybe some new features. We might talk about different algorithms that might be used, different machine learning techniques that are plausible. I think the very important thing, though, that you mentioned is the input data. And, of course, we saw that last week with the digital basal area, that the input data is important, that it be of some high quality. And if it's not of high quality, then we can do things to improve upon that. But we can't necessarily get around it in certain ways. So, Vinay, actually, we were talking about data augmentation at one point, which is a technique that people use to sort of improve the sampling of their input data. But that only goes so far. We can't magically make it a lot better. So yeah, and then so we saw with digital basal area we have we don't have the highest quality data, but we want to think about how maybe we can optimize the input data that we have. So go ahead.
We had an old lesson in computed tomography. In general, you think garbage in, garbage out. That's the general rule. However, we found in computed tomography you could have garbage in and you get a picture that seems to make sense. Okay, so you get garbage in, you still get a picture.
Yeah.
So you have to be very careful here that if you have garbage data, algorithms may still try to make sense of it.
Yeah.
And in fact, they make sense in some way that you think is wonderful, but it may be completely garbage. Okay, so it's a caution I present. The garbage in, garbage out algorithm does not generally work. It's a linear notion.
Yeah. Okay, so
especially when you're trying to do image recognition and these machine learning, because what you're trying to do is imitate what people do, and that is trying to see a pattern where there may or may not be any.
Yeah.
Okay, and so we're forcing it. And this is, I think it has its basis in evolution, because if you see a tiger that is about to attack you, and you take evasive action, you will survive. Okay? If you see a tiger and there is no tiger there and you take evasive action, you still survive.
Yeah.
Okay? And therefore, the bias towards seeing the tiger, whether or not it's there.
Yeah.
Okay?
So yeah, that's good. That's a good point. We might do a discussion on that maybe next week or the week after on input data. We have the Devo Zoo, which I'll show when we do this discussion, but it's a website where we have a collection of data from different sources, and they're compiled in a place where people can get to them quickly and explore them. And so, we might discuss that in light of some of these techniques, and perhaps talk about how, the best strategies for that. So I don't know if Jesse or Dick are interested in presenting anything in our group. If you are, let me know, and we can schedule a week.
But I haven't done any machine coding, language coding, so.
Yeah, I mean, it doesn't have to be programming oriented. Just something to facilitate discussion. So this was a demo of Vinay's project, which is very good. And then the week before we had the digital bacillary, which is kind of a mix of the coding and non-coding. So I mean, I don't want to make people feel that like it has to be hardcore coding.
Let me think about it. The bacillary project, of course, is a very high level analysis of the motion of the bacillaria.
Right.
I'm working on a paper right now, is sort of history of models of the motor of those cells, what causes them to move, and it got into some pretty subtle image processing at one point. So that as I finish that paper, maybe in a month or so, I might be ready to give a talk on that.
Okay.
Okay.
All right. And then Jesse says that he would be able to do it, probably not next week. That's fine. There was that OpenAI paper. It was interesting. So, yeah, Jesse shared a link on an OpenAI paper on, I think it was hide and seek, where they trained agents to play hide and seek, and there were some interesting things there. But maybe not as related to this. It's fine. We can talk about different models, too. It's just that there's so much going on, and not just machine learning, but in a lot of the AI stuff that, we want to kind of facilitate some discussion and see, what the possibilities are. So, so think about that, and then if you have something, and then we can maybe put a week on it where we can do it. I don't want to pressure you too much, but yeah, it's just, it would be interesting to see where that discussion leads. So thank you for everyone for attending again, and thank you, Vinay, for your presentation. And if you have any questions over the course of the week, let me know. And have a good week.
Okay.
Okay.
Very nice work.
Yeah.
Learned a lot.
Yeah.
Thanks.
Thanks.
Bye.
Bye.